I'm Jadwiga Wilkens, and I will give a lecture for you, introducing the concept of classical shadows. And I'm very grateful, and I thank the organizers for giving me this opportunity to be at this amazing conference and also to speak to you and to teach you something that I'm very excited about. But first, before diving into the science, I want to first set the stage a bit and say a few words about myself and then maybe gauge the room where everybody is from. And you can interrupt me at any point. If I don't see you, maybe knock on the armchair or something so I get a bit of an audio signal that somebody has a question. So before we start, again, I'm from Linz. I'm a PhD student at Richard's group, and I joined 2.5 years ago, where Richard actually started his group, and I'm one of the first PhD students. And we had the opportunity to, we chose a mascot for the group, the sloth. And it's a bit of a pun because our group is called Quantum Information and Computation at Kepler. Kepler is the university in Linz, which is abbreviated to QUIC. So we are the QUIC sloths. But okay, so that's our group. You can see Richard hanging there as a QUIC sloth. And I'm also very excited that one of our newest PhD members, Elena Giovannini, is here with us. And she's also working on shadows, but a bit more on an elaborate protocol with multi-copy shadows. So if you have questions on that, I think that she will be very happy to talk about that. All right, so for everybody who doesn't know, where is Linz? This is the map, the world map, and we are right now here in Natal, and Linz is up there, a little bit in the middle of Austria. It's between Vienna, Munich. You're also very quickly in Prague, in Zurich. It's not a big city, but it's a very nice city. And normally when you take the train in Europe, you will probably go through Linz. So if you just step out of the train and visit us, that would be amazing. And we also have a little, Richard and me decided on having a little challenge. So in these 3 lectures, we will derive the most simple approach for classical shadows, namely looking at linear functions in rho. And we will give you a challenge, namely derive all these equations and code the protocol for nonlinear functions in rho, namely for second-order functions in rho. And then you have 2 weeks, and everybody, if want to participate, sends us the solution with a little motivational letter and a short CV, and then Richard and me will decide who gets invited with all the travel expenses covered to our group in Linz. I will be a bit more specific during these lectures, and if you have questions, you can, of course, always approach me. So I invite you to take that challenge and visit us in Linz. And also before I start again with why we are here learning about classical shadows, I would like you to scan that QR code. And then there are 3 questions. And I would like to gauge a little bit the backgrounds of the people here, the degrees that they hold, and then also where they're from. So please scan this QR code. I will just quickly switch to the interactive mode. So don't worry, you will have another chance of scanning it. I think it's, I'm a bit new to that. Oh no, I was locked out, I'm sorry. Again. Let's see if that works. Yes, okay. Please, now it's the interactive mode. And I think you don't have to put in any names or something, you can just stay anonymous. Okay, it looks like everybody is in. I never used that, so next. That doesn't work. No. Aha. Now you should see this little survey, and you can enter your background. I see already a lot of theoretical physics. Some computer science, they're fighting, computer science and mathematics. Ooh, some engineering. All right. Okay, it looks like we're a lot of theoretical physicists here. Not so surprising. And I can see that we're already 56 participants. That's also nice to know how many people we are. Very cool. Okay, good. So it looks like the majority of you is theoretical physicists. Then we have some computer scientists, a little bit of experimental physicists, some mathematicians, and some engineering people. Very cool. I'm having a background in physics, but now I'm working at the computer science department. So I'm actually, on paper, a computer scientist. All right, let's go to the next. I don't know how. To the next question. So what stage are you in your studies? Either you're right now doing your bachelor's, you're doing your master's, you're doing your PhD, or your postdoc, or others. I don't know if you're a professor like Richard, I think. The question if you're still studying is maybe not the right question. Okay, a lot of PhD students. I see a lot of master students too, some bachelor students. I would not have expected that, to be honest. I was too shy as a bachelor student to go anywhere. And also postdocs. Okay, very cool. So it's less than half PhD students. That's also interesting. Interesting to know. I would not have expected that. And now let's go to the last one. What country are you studying in? And this is a word cloud, so you can put in the country. And I don't know if it's case sensitive. So maybe just everybody, okay, I see you're already putting in countries. Okay, lots of people from Brazil, cool. Germany, looks like the second biggest. Very nice. Okay, that's not so many countries. I would have expected more. So Brazil, Germany, then Argentina. Ooh, Japan, very cool. United States, Korea, Russia, Argentina. Very nice. So now we see a little bit where people are from or where they're studying in, right? And yeah, with that, one participant typing. We should wait for that participant. Should we? Okay, cool. Very interesting to see that. Thank you for sharing. Then I would say that we go back to the presentation. Okay. And I will be very transparent in what we will do in each lecture. And I think it's very important to make the goals clear in order for you to know what we are doing and when. So this is the plan. We have 3 lectures. And in the first lecture, I will give you a quick overview. Why do we need classical shadows? Then I will go into the basic notations, what we will use. So what's a cat vector? What's an operator? And there I would like to take the liberty to introduce a way of thinking about operators and tensors, namely in tensor diagrams, where we just draw little boxes and connect legs. And with that, we don't need to calculate complicated sums over some indices over some operators. It's not necessary for this lecture to understand this tensor diagram language, but I think it's a cute way to be introduced by it and maybe to learn how to love it too. So this we'll do in the basic notation. Then we will quickly go over the single qubit Pauli measurements, why they're important and why they're very cool. Then I will quickly explain to you what one of the most plain state tomography protocols are and why they are not feasible for a higher number of qubits. And then from that go to the start of what classical shadows are, where we need to revisit what a measurement is. We will derive what the measurement channel is, and then we will do the linear inversion of the measurement channel. This is mostly for 1 qubit. It's a bit easy. It's a bit, maybe on the blackboard, I will show you some proofs where you can, again, always interrupt me. And then in the end, when we have some time, I can show you a bit what I like about channels and how we can represent them as a matrix, but only if we have time in the end. And then in the second lecture, we will go to multi-qubit measurement channel, which is a little bit more involved. And we do need to calculate with some indices and pull out some sums and take care of how we represent our quantum state. Then I will introduce to you quickly what a vector T design is, because we need that for the global Clifford measurement channel. Again, linear invert these measurement channels. talk about what are observables and how we can write them in a mathematical and useful way, and then talk about the classical shadow protocol. And I would love to code the protocol with you, of course the easiest case, but I will prepare some live coding Jupyter notebook that I will then fill in with you so that you really understand step by step that the classical shadow protocol is actually a very easy to implement, very intuitive and very useful protocol to use in your research. And then, so this is more hands-on, a bit more coding, and then the third lecture will be a bit more mathematical heavy, where we will see, I have a classical shadow protocol, how do I know that I actually converge to the true value? And there we will dive into complexity bounds, different types of them, and then what we have to use in order to calculate the Bernstein inequality for our classical shadow protocol. Namely, we need to know the variance of our estimator. This will be a bit more mathematical, a bit more involved, and then we will derive the sample complexity. So how many samples do I need to get out of my machine to be sure that I'm very close to my true value? The third lecture will be a bit more mathematical, but I hope that until then we're all set. Also, there are some lecturers who will introduce to you what representation theory is, for example, so maybe you can already use that knowledge. Let's see. All right, let's start with the overview. What are classical shadows? Why do we need that? And I always like to think in quantum computing, there are 4 stages. So the first stage is I need to formulate a question that I can run, where I can solve it. I need to formulate a problem that I can solve with a quantum computer. The second stage would be formulating this question as an algorithm. It needs to be machine. It needs to be something that a machine can read and process. And the third stage would be then to execute this algorithm with a quantum hardware. Normally, there's some feedback loop, and we also need classical hardware to work in symbiosis with this quantum computer. And then hopefully the last stage would be find the question to our problem. And this for me is just roughly the 4 stages of quantum computing. Again, I'm now a computer scientist with the background of quantum physics. So for me, it was a bit useful to think in these terms. And then what are the problems that people are looking at right now that are interesting to solve in this way? Well, one of them, and now the physicists in the room will probably not, is we want to find the ground state of a certain Hamiltonian. And for this, we need to calculate the expectation value of a given Hamiltonian with a given quantum state that is implemented in the hardware. So we need to actually many, many times measure our quantum state to calculate such an expectation value. Then also, maybe more physics related, look at spin-spin correlation in a spin chain or a 2D spin plane, and look how my system evolves under a certain magnetic field or some interactions between my spins, also expectation value. It also can be interesting to look at how close are two quantum states to each other for quantum system verification maybe. This is the equation for if we would have 2 pure states. This is the quantum state fidelity. Also something where we actually have to measure many times in this kind of protocol that I will introduce. And then also we have nonlinear functions in rho. So back until now it was only 1 times we had a rho. Now we have rho square, where, for example, we want to infer the purity of our quantum state that can give us information about the entanglement or how mixed my state is. And then from that, calculate the Rayleigh entropy. So these are all in a sequential measurement protocol with only 1 copy of our quantum state. These are protocols where I need to many times prepare my state and then measure and then estimate probabilities. There are also other protocols that don't need that. For example, the very famous Shor protocol, where we actually, in theory, only need 1 shot from our prepared circuit to infer the prime factors of our number. Or let's say not just 1 shot, but just a few shots, but we don't need to estimate probabilities here. And sometimes it's also useful to just have access to the samples of the quantum state to maybe train a neural network or something like that. But we will not talk, but classical shadows are not, they're also useful in these things or in the last one, but we are more concerned about these expectation values. So this lecture will be about the readout stage, because in this execution phase, you first need to input classical information into, or encode classical information into the quantum system. And then after we run our algorithm, we need to extract that information from our quantum system. So we need to bridge the quantum realm with the classical human readable world. And classical shadows is a great tool to tackle this readout problem. All right, now you got the big picture, why classical shadows, it's a readout protocol. And now I want to quickly start with you and look through some basic notations that we will use throughout the course. The most common one, and we all use it, I think, is the cat vector. It lives in a Hilbert space, and we normally denote it with this bra cat notation. And now I will already start to introduce you to this diagram notation, where a vector is just one box with one leg pointing to the left. So when I write down diagrams, I always think in mathematical order, so from right to left, and not as we are probably used to from left to right, so the time order. So always when you see a diagram, how to prepare a quantum state or something, you have to read the circuit from right to left. All right, so a vector is a box where the leg sticks out to the left, and it means that there's one index that we could sum over. This would be a column vector with, d many entries. Then we have the dual to that vector, the dual vector, which we now denote as this bra notation, so the flip version of it. And it lives in the dual Hilbert space, and the diagram would be now sticking the leg to the right, because now if we want to calculate some operator acting on this vector, we need to multiply from the right. Then one special case of these cat vectors is a pure state, also a cat living in a Hilbert space, and it has a condition, namely that the inner product with itself has to be 1, meaning that we can interpret the entries as probabilities or as amplitudes. And in my beloved diagram language, we would have to take these two vectors and then contract the leg in the middle, meaning that we sum over that index, and this has to be 1. This is now a number. There's no leg sticking out, so that's not a vector or anything, it's just a number. Going a level up, we have operators. Operators are actually linear maps, taking elements from a Hilbert space and spitting out elements that live in the Hilbert space. And so I denote this as L, so the linear functions on H. And now we have, as I said, we have one input. So this would be the right. And then we have one output, that is the left leg. So now there are two indices to sum over. That's an operator. And we again have special cases from that. So for example, we have the density operators. These are a special case of these linear operators. Namely, they have 3 conditions. They need to be Hermitian, so rho equals rho dagger. The trace needs to sum up to 1. Again, the diagonal can be interpreted as probabilities. And it has to be positive semi-definite, meaning that the eigenvalues cannot be negative. In our diagram language, taking a trace means that we have to connect the input and the output leg and then contract over that index. Again, this is a number because it does not have any legs that we can connect to and sum over. And another special case is the gates that we use to manipulate quantum states. They also have to have a condition, namely they need to be unitary. They preserve the conditions of our quantum state, meaning that they are that they don't map our quantum states out of the space that we need them to live in. And here it's U dagger U is equals to identity, and again in tensor network language this would mean, because we know that it has to be identity, we just write the identity as a straight line. And because we also talk about multiple qubit states, just to show you, so our multiple qubit vectors live in the n tensor fold of our Hilbert space, and then that means that we have n legs to connect to, and in the operator case it's the same, we have n legs on the left and n legs on the right. Okay, now I would like to show you some examples, and I would like to do that on the blackboard. Let's see how that works. Has anybody seen this tensor network language already, or is it new to everybody? Who has seen and used it already? Oh, okay, a bit less than half of the people. Okay, so let me just show you quickly. The microphone sounds a little bit weird. How the maths is behind contracting two legs. So if I would tell you I want to calculate my evolution, my unitary evolution of some pure quantum state, I could look at the ith column index of that. And then probably, as you all know, this is the same as looking at the unitary which has 2 indices, and then also looking at my quantum state, and we have to sum over the jth index here. This is just matrix vector multiplication. And in our diagram language, we would have U, so it has 2 legs. And then we have our psi, which has 1 leg. Let's call it K for now. And if we connect them, that actually means that we write delta JK. So this becomes a J, and then we have to sum over this index that we just changed with them. That's everything about contracting these legs. And for 2 operators, so if we have now 2 operators, it's the same, just with more indices to sum over. So we would have Uij and then Vjk. And in our diagrams, this would look like this. Good. I need to look at my notes. Okay, I already told you how this tensor looks like in multiple qubits. So we have just a huge bag with a lot of legs. But if we have a specific structure of our, for example, unitary W, I don't know if you can see from this side, maybe I go like this. For example, we have one unitary that is just one unitary tensor, the other unitary. Then we would write that, as I just told you, an operator with 2 legs on the right and 2 legs on the left. But we have a specific structure here, so we can just write our U in the top part and then our V on the lower part. And this means that there is actually like a tensor product in between this, which we will never write. So if we have 2 operators over each other, there's always a tensor product in between them. And now, last but not least, 2 more things. How do we transpose an operator? I always find that kind of funny to look at. So if I have my operator A, I want to transpose that. Then I have, I don't have so much space. A transpose input and output is the same as swapping the input and the output legs, which kind of looks funny because I need to swap the input and the output legs. So this one now points to the left and this one now points to the right. And the last one that will be important for this lecture is a specific operator, namely the swap operator, that acts on 2 tensor spaces. And just intuition wise, we have 2 tensor spaces, and then we can just swap them such that 1 goes mapped to 2 and 2 to 1. This is just the swap operator where you probably know the matrix for, which just looks like this. You mean here? Yes, not a joint. If we would have a dagger here, this is transposition plus conjugation, right? Then we would need to keep track of the conjugation, because this our tensors do not keep track of for us. So only transposition is bending around the legs. The conjugation we have to keep in mind. Good, thank you for that question. All right, any more questions? No, good. Oh, my laptop went out. Yeah. Okay. Good. So this is our basic notation slide. And what we are concerned in this readout stage is actually the quantum states, right? This rho, this mystical density operator that we always call rho. And in this case, it's just abstract mathematical object. So if I give you a qubit, a simple conducting qubit, and I tell you, please tell me the quantum state that I prepared here, what is it? You will first be like, I don't know, I can't just look inside and tell you. I need to measure it, right? And I find it very instructive to always look at the Bloch-sphere in the single qubit case. And I hope that you all heard about it. You're almost all physicists. And I think it's a very physical way of thinking about a quantum state. So we have here 3 axes. And these axes correspond to the Pauli operators, the Pauli matrices. We have the z-axis, we have the x-axis, and we have the y-axis. And then we have this unit sphere around this axis. And every time when the axis pierces this sphere, then we know that this is actually the vector for one of the eigen basis vectors of this respective Pauli. So we have 0 and 1 for z, plus and minus for x, and I plus and I minus for y. And because we know that the Pauli matrices they form a matrix basis for the Hermitian operators, we know that in theory, in mathematical expression, we can always write each quantum state, single qubit quantum state, as this linear combination of Paulis weighted with their overlap with this quantum state. And that's already great. Now it's not something very abstract, it's very hands-on. We have a Pauli matrices that we know how they look like, and we have some scalars, some numbers, trace of rho with this Pauli word. And if we would now have access to these scalars, then we could, in theory, reconstruct and write on paper how our quantum state looked like. And I first want to quickly show you that we can prove this without using that it's an eigen basis for the Hermitian operator. We can prove that this is true. And I think it's very instructive to do so, because we will use the tensor diagram language to do so. Can everybody read this board when I write here? Okay. All right. So we look at the single qubit Pauli decomposition. Qubit Pauli decomposition. I will just copy what I wrote there, so we can write every quantum state rho as 1/2 times the sum over all my Paulis times trace of rho, I want to write Pauli rho, weighted with the Pauli operator. And here the trace object, so the trace in our case just means when I take a trace over some operator A, I'm actually summing over, in this case, just 2 basis vectors, 0 and 1, over the diagonal of A. In our language, this was this, right? We just contract the input and the output. And there's another thing that we can do with the trace. We can define partial traces. So a partial trace is a trace that we only take over specific subsystems. And because we will need that now, I will define what the partial trace of the first subsystem is. So the first subsystem is given 2 vector spaces, 2 tensor spaces. And this is defined as, again, the sum over my basis elements. And I want to only sum the first space away and not the second. So I insert an identity. I want to do anything on the second space. Again, first space, nothing on the second. And this is actually trace of A times B. Yeah? And maybe you see already we have such an expression there. So we can just reverse engineer and write this expression that we have here with the partial trace. So again, my sum over my Paulis. Why did I do that? And then a partial trace of P rho tensor P. We just used what I just showed you there. And now we can imagine that there's an identity here, and we can pull out row tensor identity. P, tensor P, times row tensor identity. Now we split away the part that we're summing over from the quantum state, and because the trace is linear, we can just pull in the sum here. So this would be the same as, okay, I will rewrite it. Sum over my Pauli, 1/2, and then our trace around that. Okay, so we really just split this term into two pieces. One piece where we don't know what row is, right? We want to infer that. And the other piece is this expression here, where we sum over the Pauli tensored with itself. And this is something that we can just calculate using the definition of the Pauli operators, right? So I don't have so much space. Let's see. So now you need to help me a bit. So x tensored with itself is, so x 0, 1, 1, 0 is a 4x4 matrix where we have a 0 block, top left. Then we have 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, and then 0 again. I hope I'm not boring you. Maybe it's a bit too easy. Then we have y tensored with itself. Now you need to help me. Who can tell me what the tensor product of that is? Nobody? Yeah, 0, 0, 0, 0. Okay, what is that? So y minus y times y. Very good, like this. Okay, and then in the bottom left, what are the two? The same? No. Exactly, right? Because we take this times I, not times minus I. So we have 1 minus 1, and then 0 again. Thank you. And now, last but not least, we do this with the Z operator. And I think this is very easy to see. We just copy the diagonal and then take it times the respective entry. So this is the Z operator, bloop, with the zeros in the blocks. And then, of course, we have the identity that we shall not forget, but that's just once. Okay, and we are now summing over this in this expression here. And as you can see, this value is canceling with this value. So the top right and top left corner, they're just being cancelled away. And then we can also see that these numbers here are being cancelled away. So the one in the middle. And what stays is these entries here and these entries here. Whoops. In the next to the diagonal. And because we have a 1/2 before the sum, we actually get out the operator that I just told you will be important in our lecture, which is the swap operator. Can you see that? I don't have so much space on the blackboard, but if you now sum over them and divide by 2, you will actually get this operator here. So that's great. We know it's the swap operator, and we know how it looks in diagram language. So a little space. Let me just. So I want to now express this thing in our diagrams. And we can see in the lower line that we have row tensor identity, which is just writing them on top of each other. That's row tensor identity. And then I have my two Paulis on the left. So here's one Pauli, and here's another Pauli. And we are summing over them. So that's an index, so we need to connect them. Loop. This means summing over the Paulis or summing over the index. And then we have the trace over the first subspace. which means we disconnect the upper part. And what we just did right now is look at this term here and saw that this is the swap operator. And I just told you how the swap operator looks like. So this diagram actually simplifies to inserting, instead of this, the swap operator, loop, loop. And it's just a lot of legs that are just crossing each other, but that doesn't matter because I can see that this leg here just has one loop where then it ends up in the same direction. So I can just delete it. I don't care about this going around. And this leg here also is the same direction. I don't care about this curve in here. I can just kind of retract it and pull it back. So this in the end is just my quantum state. So we just proved, without using that it's a basis, that the Paulis are a basis, that this expression up there is a valid expression. I find that cool. It's kind of cute to look at that. Oops, this way. Do you have any questions? No. And this was just a little, showing how we can use this language. It will not be very relevant in this lecture, and I know that you all believe me that this is true. It was really just for the sake of, getting a bit warm in our mathematical fingers. All right, this is also true for the multi-qubit case, where we now need to sum not only one Pauli, but the tensorfold of all the different compositions of the Pauli matrices, which in this case is 4 to the power of n many scalars, Paulis. And up there, I forgot to say that the identity, the scalar when we do trace of row identity is actually always 1 when we look at valid quantum states, right? So here, in the single qubit case, we have actually 3 values that we need to characterize. The trace of row X, trace of row Z, and trace of row Y, which are the expectation values with the Pauli matrices. And how would we do that now? Again, I gave you a qubit. How would you measure these expectation values when you have this physical device? So let's dive into what are measurements. And normally in a device, I think all the hardware that I can think of, the native measurement that is there already is the projective Z measurement. So you get a qubit, you read it out by either sending some microwave pulse, or in an ion trap sending some laser that reads out if it's bright or not. Normally it's a projective Z measurement. So either when we do this measurement, we get out a 0, which then collapses the quantum state onto the 0 state, where we can now say that the probability that this will happen is just the overlap of the 0 state with our quantum state. And the post-measurement state after that destructive measurement would just be the outer product of the zeros. Or we can get a 1, where again, same gist, the probability to measure a 1 is just the overlap with the post-measurement state in our quantum state, which is 1 row 1. And the post-measurement state would be the outer product of the 1 state. All right. And we know the decomposition of our Z matrix. Our Z matrix is just 0, 0 outer product minus 1, 1 outer product. If we take the trace with our row, we see that these two probabilities that we really have direct access to, if we just measure many, many times, are in there. And even better, we only need to estimate the probability that we're in the 0 state, and from that we can infer the expectation value with the Z Pauli. Great, 1/3 of your task is solved already. Now, what happens if I want to measure in the Z-axis? Right, we only have access to the Z. What happens if we want to measure in the X-axis? We only have access to the Z measurement. And because the trace is cyclic, we know that if we apply a unitary to our quantum state, it's the same as applying the Degard version to, well, the expectation value that we want to measure, as you can see here. So we just loop swapped around this U and then have U Degard Z U term in here. And because we want to look at the expectation value with the Z matrix, we know that U Degard Z U has to be X, or for the Y measurement, U Degard Z U has to be Y. And this should look familiar for you. because there's a very famous group of operators, namely the Clifford operators, that map Pauli matrices onto Pauli matrices by exactly this action of conjugation. So we will now look into the Clifford operators. And in the single qubit case, there are 24 of them. And they are defined such that it's the operation that maps the whole Pauli group onto itself, where we don't care about global phases. These will, in the single qubit case, are 24 matrices, and I took the liberty to write down for you in the Hadamard and phase gate decomposition what these 24 Clifford matrices are, because I was always annoyed when people talked about the Clifford matrices. Nobody really wrote them down. It was just this abstract definition. So I just sat down and coded that for you. And we can see that here's like, I found a little of a pattern. So on the left, we have these like identity or S or SS or SSS. And then when we always add a Hadamard to this one, we go into this group. So Hadamard S goes here, Hadamard SS goes here, Hadamard and Hadamard cancels, so then we have SS Hadamard and so on. And then when we add an S gate to that, then we arrive in this group. That's somehow how I found these Clifford matrices. And now we want the matrices that, or we just need one that maps the Z Pauli matrix onto itself. This would be the Z measurement. Then we need one, which is obviously the identity. Then we would need one unitary that maps the Z matrix onto X, and then one that maps X onto Y. So we just need to pick two of them. And I already worked that out for you. These are finally three groups where this is, I call it the Z stabilizers. I don't know if this is the term, but all of this by conjugation leaves Z invariant, except of global phases. Then this group here maps Z always to X, and this group here maps Z always to Y. So we just need to pick, let's say, the first row, and this will implement our Pauli measurements now. And you can see here now that if we measure trace row HZH, we actually measure trace row X, and the same goes for Y. And now we need to watch out a little bit with the dagger, because we had to pull the U to the right, and now we cannot change the measurement axis in our device. We can only change our quantum state. So now we need to kind of bloop, move them back in order to prepare our quantum state and then measure in that respective basis. And just to give you a little heads up, we will also use the global Clifford group, which is defined on not just P, but the n-fold of our Pauli group. And this is just the same definition as above, just with all the Pauli strings. All the Pauli strings are being mapped on all the Pauli strings. This is the global Clifford group. All right. So now we know if I want to measure in the X basis, I just have to apply Hadamard to my quantum state. And what happens then is, if I do that, my conceptually, my measurement axes change. The X and the Z axis swap, and the Y axis actually changes direction, which we don't care about because we only have access to this axis here, right? But now if we measure our state, we would have the same as above, just in the X basis. So measuring a 0 would actually be measuring a plus, measuring a 1, down there would be measuring a minus, and then our post-measurement states look like autoproducts of plus plus or minus minus, and we can rewrite our expectation value again with just estimating the probability to measure plus in this case. Same goes for the Y measurement. What happens here is actually we need to apply S dagger H to the quantum state, and then our measurement axes are kind of permuted, and now we would measure in the Y eigenbasis. And with that, we have access to our expectation value of our Pauli matrices. And with that, you solved your task. You can just prepare many times the Z measurement, and then measure many, many times, estimate the probability that you get 0 for the X for the plus, with the plus, and then for the Y with the I plus. And then you could estimate the probabilities, the scalar values, in front of your quantum state decomposition. And in general, a quantum state tomography protocol would look, and this is the most and easy one, there are of course so many various variants that are much more elaborate and better, but this is one of the most plain quantum state tomography protocols that I could think of. So for every U in these three U's that we just looked at, we first prepare our quantum state, we apply our rotation, which for the Z is doing nothing, but it's also a rotation. Then we perform the computational measurement, and we need to save the outcome, and then we repeat this many, many times. After we've done this, there's a post-processing step. So we need to estimate these expectation values, so that will be prone to shot noise. Then we are reconstructing our shot noisy quantum state. And because of the shot noise, we are not sure that this reconstruction is a physical description. And I can tell you that mostly it is not. Mostly it has negative eigenvalues, and it has not just one small negative eigenvalue, but it can have a lot of negative eigenvalues. So this is not a valid quantum state description. But we already said, no, we need a valid quantum state description in order to calculate all our Hamiltonian eigenvalues and spin-spin correlators or something. So there's an important step that is called projecting this reconstructed state onto the valid set of quantum operators. And I think the most common protocol to use for that is the maximum likelihood optimization, where you need to solve a lot of linear constraints in order to project the state into the right subset. So once you have done that, you can estimate everything your heart desires with this quantum state, everything that you learned in your quantum information class. The world is open to you. And this is now for the single qubit case. And for the multiple qubit case, we see that we not only have to look at only three U's, but 3 to the power of n many Pauli words that we need to estimate, that we just apply in a tensor network structure to our quantum state. And then we need to, of course, take into account the multi-qubit decomposition. And now you can see already this scales up exponential in n in two places. The first place is we have to estimate 3 to the power of n many Pauli words, which is a lot. And then this in the post-projection, so first of all, we need to reconstruct a 2 to the power of n times 2 to the power of n matrix that has complex values. And then we need to solve a linear optimization, linear constraint optimization algorithm with this huge matrix. And I don't have to tell you, I mean, you probably know, but this scales horribly. For 10 qubits, I think 3 to the power of n is, I don't know, something like 100,000 something values. And then 4 to the power of n is already a million. And that's only 10 qubits. You will fry your laptop, or maybe even some CPUs and GPUs, if you go to higher qubits. So this is not feasible at all. And if we would stop here, we would say, okay, quantum computing is dead. We cannot infer what our quantum states looks like anyway. Okay, bye, whatever. But the good point is that there are ways around that. Namely, one of them is called classical shadows, where we do not need to reconstruct our whole quantum state, and we do not need to impose a physicality constraint, and still everything what we want to do, in this case, estimating linear functions in rho, still works out. So a little outlook. Now you got the motivation. Why do we need classical shadows? Just check the, okay. Why do we need classical shadows? And now I tell you how we will get them. And this is just a quick overview. So in general, we have a sequential measurement protocol where we prepare a quantum state and then apply a measurement ensemble layer to that and then measure in the computational basis. And this we will do many, many times with possibly random unitaries here. From that, we can calculate the so-called measurement channel. So what happens actually with the state, like in the device, if we do this many, many times on average, we will see that it's actually a very structured and easy channel that we can calculate. We can invert that channel in post-process, and then by inverting that, define what a single snapshot or a classical shadow of our quantum state is. With this single snapshot, we can also estimate everything that we want. And then in the third lecture, we will calculate the variances. So how bad is our probability distribution? How far away are things? And then from that, we can infer the sample complexity. How long do I need to wait in order to be sure that I estimated my values that I wanted to estimate. And I don't want to scare you, but this is the table that we want to fill in. So we have single qubits, which is the most easy one, and we will use it as examples. Then we have multiple qubits with local Clifford measurements. And then we have multiple qubits with global Clifford measurements. They are very different, these two, and we will see why and how. And maybe I don't have time to go over all of them in detail, but I just want you to see this is what we'll do in the next 2 lectures. And I also want to point out there's something in the middle here that I will not talk about, which is called shallow shadows. But this will not fit into this scope of this lecture. Okay, good. Let us dive right in. Maybe I just first ask, is everybody still with me? Good. Do you have questions? No, this is always a bad question to ask because people want to progress fast and then they never raise their hand. Okay, anyway, so we will now look at the measurement channel. What is this mysterious object in the case of single qubit measurements? And this slide looks familiar to you, right? We just used that. And instead of calculating these expectation values, so I don't care about the post-measurement state, what if I care about the post-measurement state? What if I want to look at what happens after my measurements on average in the hardware? And this is characterized by the so-called measurement channel. And we can define 3 measurement channels here. They're always characteristic to the measurement ensemble that you chose. And in the Z case, it's a channel so a channel is again a linear object that takes in operators and spits out operators. So it's again a linear function on the space of linear functions of the Hilbert space. And here we can see that it takes in a quantum state, rho 0, 0, rho 0, 1, rho 1, 0, 1, 1, rho 1, 1. And then it spits out a quantum state where it kind of erased all the information about the phases that are stored in the off-diagonal term, so up there. And this is, in a bit more physical term, a total decoherence channel. We forget all the information about the phases. This would be the measurement channel in the Z basis. You can do similar calculations for the X and Y basis. So these are 3 channels that themselves do not preserve all the information in our quantum state. They forget about certain information, which is bad. If we look at one of them and we only calculate the Pauli Z expectation, we don't have all the information right of our quantum state. But what we can do now is we can look at the combination of these 3 measurement channels. Namely, 1/3 of the time we measure in Z, 1/3 of the time we measure in X, and 1/3 of the time we measure in the Y basis. And in a bit more mathematical terms, this would be a sum over 3 terms. So we have the 3 unitaries with which we prepare the Pauli measurements, and then each of them has a 0 or 1 outcome. And this measurement channel looks a bit complicated. And it looks like it depends on rho, right? Like it kind of depends on when I put in a rho, maybe another thing will come out. And I will show with you now together that it's not the case. And that it's actually a very easy and structured channel that comes out here. How much time do I have? Okay. Please. Mm-hmm. 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 I mean, in metrology, mostly you probably have a very specific problem that you want to look at, right? So if you have a very specific observable, for example, only the Z correlators, and then, I don't know, you want to see how that looks like I don't know so much about metrology, or you want to see how some angle, how your probe is being turned, so you want to look at that angle. And there, it probably is better if you look at where is my information encoded, and how can I design my measurement to extract that information. But then it's a measurement protocol that is very specifically tailored to one specific question that you have. In classical shadows, we want to make it independent of the observable that we want to look at. Yeah, did that answer your question? Okay, good. All right, so now we look at the measurement channel and see that it's actually a very easy channel. And I will write now on this board here. and try to write a bit smaller and tell me if I write too small, okay? Because I need a bit more space now. So I will just copy this equation here. Sum over our U, which is either identity, Hadamard, or Hadamard as dagger, and then our bits. And then we have our trace with the post measurement states, U row, weighted with the post measurement states. Very good. And this should look familiar to you. We just had the similar expression right like before. So what we can do again is imagine that there's a little identity here. We can pull in this whole expression with the tensor product, make the trace partial over only the first subspace, and then again, because everything is linear, we can pull in the sum here too. Good. So this is the same as 1/3. Now, partial trace over the first subspace. My sum, I will not write that out anymore. U dagger B U. Tensor with itself. And then this, we shall not forget, acts on row tensor identity. Did I make anything wrong? No. Very good. Again, we successfully detached the thing that we sum over from the quantum state. And this is, again, something that we can just do by hand. And I'm too lazy to do that on the blackboard. And because I want to code with you in the second lecture, right, I thought, why not just code this and look at it? And let's see how my live coding skills are doing. So I have a little Jupyter notebook here. I will create a GitHub and then upload it there. And then next lecture, probably I will show you the link to this GitHub. It's a little bit small. Can I just zoom in? Yeah, can everybody see? It's a bit pixely. Okay. Sorry? A bit bigger, like this. Perfect. All right, so I will use in this lecture, when I code, I will not use any quantum package. I will not use Qiskit or Pennyline or anything. I will just do everything with matrices and vectors. And I love NumPy. That's why I always use NumPy. And I already took the liberty to define the things that we need in this lecture. So we have the 3 Paulis with the identity. I will call this list just Paulis. And then we have their eigenvectors. So cat0, cat1, cat plus, cat minus, cat I plus, and cat I minus, which I again pull together in one list of eigenvectors. And then maybe we will need the Hadamard or phase-gate, I don't know. So here we see, I just copied the term that, oh, I forgot to, yeah. I just copied this equation here, so we want to look at this, this sum here, right? And it's just 6 outer products of vectors that we tensor product with itself, which should be easy to code, no? So let's do that together. We need to store our results somewhere. I would just do this like this. I've never coded in life. Okay, then we need a for loop over all our eigenvectors in eigenbasis, I think I called it. Alrighty, so now I want to calculate the outer product, so I will just use the NumPy built-in function for that, which takes care of the transposition but not the conjugation. So I need to still conjugate the right part. So this is my outer product. And now I want to take this tensor itself, right? So we have outer product with itself. Please tell me if I do a mistake. I never did this. So some eyes watching me is maybe not bad. And now we want to average over there, like this. Good. Now we shall not forget the 1/3 I want to take care of. I want to pull it in. So this is here. Oops. So then after we sum over it, we need to take care of that like this. And then with that, we can now look at our result. Print. Yeah. Did it work or not? Ooh, it worked. No, it did not work. Why didn't it work? I don't know. Good question. I don't know what. We don't want to pull into the 1/3. I forgot. I'm sorry. Without 1/3. Yes, we don't want to pull in the 1/3. We want it in the decomposition, but not in this one. Sorry. Okay. Phew. So now we have a matrix here. Let's look at the real value. And this should again look kind of familiar to you. Who can guess what matrix this is? Richard. Very good. It is a linear combination of the identity matrix and the swap matrix. So we just showed in code, because I was lazy, that this is actually a sum of identity of the swap operator. I told you it will be important in the beginning with the identity. Ooh. And to just give you a little outlook, this is always the case. So always when we have a set of vectors that forms a so-called vector T design, or in this case 2 design, the sum over the second moment will always be identity plus swap. But we will look at that later. It's just that you already heard what that means. In this case, it doesn't really matter so much. All right, so now we can just replace this. Loop. This acts on row tensor identity. And now we have 2 sums here. I will just pull them out. So we have trace over the first subspace swap 2, 1 acting on row tensor identity plus 1/3 trace over 1, and then identity times this is just row tensor identity. And I know it's a bit trivial now, but I just want to show it in our diagram language. So again, here we have row tensor identity on the right, row tensor identity. Then on the left, we have the swap operator. Now we know how it looks like, right? Loop, loop. And we take the trace over the first subspace. And this is exactly the same expression that we had before. So this is just row. And the second term should be now very easy to solve for us. We have row tensor identity. And then we take the trace over the first subspace. So this is just, well, trace of row times identity. Okay? I see Richard is nodding, but I know that you know. Did I confuse some people? I did not? Okay, who's confused by that? You are a bit confused. Can you tell me what you're confused about? Ah, very good. Yeah. So the trace. Where do I? Oh, there. So if I have a, I mean, this trace of row is the sum over the inner and outer product, right? So this is really just connecting these 2 legs here. And connecting what leg really just depends on in which space I am. So if I, for example, would have trace of A tensor B, and now this trace is over everything, not just the first subspace, then you could write this as A tensor B. And now taking the trace is actually just connecting all, like in the same row, connecting the open legs. So the trace doesn't matter, it doesn't care where the legs come from, it just connects the right one. And I mean, this we know, right? This is just trace of A times trace of B. So if we have this partial trace, which tells me I only want to take the trace, I only want to connect the legs of the first subspace, then this really means that A, B, like in an algorithmic expression, this really means only connect the legs that are in and out in the first space. So this would mean really just connect these legs here and leave these ones like they are. So this is now a number times an operator. And the mathematical description is like up here. So I only sum over the first leg, but the second legs I just leave intact. To be in the right dimensionality, I need to add the identity. Did that help? Okay. Thank you for the question. Yeah. Mm-hmm. Mm-hmm. Mm. Good. The purpose is we want to see if we find that this channel is maybe not that complicated, it has some structure, and we can invert it easily. Because this channel, how I define it here, I would not know how to invert it like Mm-hmm. It's all three. So it's really a protocol where I want to measure in all three bases in a uniform way. Yeah. And as I said before, only measuring in the Z basis, we lose information. Only measuring in the X basis, we lose information. But if we do all of them together, maybe we don't lose information, but we don't know. We will see. But good, thank you. All right, so again, this part here is row tensor identity. We swap these two legs here and then take the trace over only the first subspace. And we can see again, so right, I wrote this expression down again, that the right leg here, it's still like, if I go here, it still points to the right direction. We don't care about loops, so we can just retract this leg. The same with this, we don't care that it points down or not. So this is really, again, just row. And the other term, I will just write it down again, is row tensor identity. And then we take the trace over the first subspace. So this is just trace of row tensor identity. And if I insert that here now, yeah, this is 1/3 row plus 1/3 trace of row identity. And maybe some of you, yes? Why? Good question. We are not tracing the identity. If we would, but I also did that mistake when I did the calculation first, because just imagine that we have this and we have the swap on both. Let's just imagine, yeah, we have swap on both spaces, like this, which we don't, but just. And now we would take the partial trace. Then we would get trace of identity, so a loop, which is 2 times row. So this diagram would actually be trace identity times row. But back here, we are just connecting legs in a funny way, and we don't have a closed loop, which would be a trace of identity. Yeah, you get that? Cool. But I did this mistake in the beginning too. I was like, doesn't there have to be a 2? Okay. Good. Now we have this expression here. And maybe some of you are like, this looks a little bit similar. And I will just do a little trick. I will take my right part times 1 times 2/2. And then I see that this one is actually the maximally mixed state. Identity over 2 is the maximally mixed state. And 2/3 actually is 1 minus 1/3. So what we have here is now 1 minus 1/3 trace of row, and then the maximally mixed state. And this here is a very well-known channel. This is the so-called depolarizing channel, where with some probability or depolarizing parameter p, we always end up doing nothing. So we end up mapping row to row, but with a probability 1 minus p, we lose all the information of our quantum state and map our state onto the maximally mixed state. This is a very famous channel that I, for example, use a lot in my characterization of hardware, because this captures very well what happens in a real device. When you couple a little bit with the environment, you lose a little bit of quantum information by coupling to the environment. Then this is a good channel to approximate this physical process, the depolarizing channel. Who has already seen the depolarizing channel? A lot of people. Very good. Okay. So we have just shown that actually our measurement channel is just a depolarizing channel with the strength 1/3. Right? That's a very easy and structured channel. That's a nice result, no? Because I know very well how to calculate with it. And we very successfully filled in our first tile. Whoop, whoop. And now, as I told you, we also want to invert. We have 10 minutes left. We want to invert that channel now. And this slide is not very pretty, I'm sorry. But since we know in this case that, so inverting a channel means if I act with my measurement channel on row, I then want to act with the inverse of my measurement channel until the object that comes out, and then I want to get row out. This is how I define in a very non-mathematical way the inverse of a channel, and this circle means just like composition of channels that we applied after each other. And because we just derived that our measurement channel is the depolarizing channel, this goes for the depolarizing channel, right? And I'm very sure, and I can tell you that we will find a p prime that when I concatenate that with the depolarizing channel with the strength p, that this will actually cancel each other and then give back the quantum channel row, which is, I mean, it's not trivial, but I just make that assumption here. And we will now quickly go over what is this p prime, such that my depolarizing channel with p prime acting after my depolarizing channel with p always gives back rho. This will be our last calculation for my lecture. And yes, okay. So inverting. Good. So I want my dp prime act on this thing here. And I want this to be rho. And now for which p is this, for which p prime is this the case, right? And this is just, you know, we just write it out. It's a bit boring, but I just want to take you on that journey. So we can write this as p prime, and now I will write this also out. So we have p rho plus 1 minus p trace of rho, which is 1, divided by 2, identity. The channel is linear, so we can write p dp prime acting on rho plus 1 minus p half trace of rho, which is 1. We can just scrap that. We can just not write that. This one acting on the identity. Right? Maybe it's a bit too easy for you, but I think in the end of this lecture, it's nice to see something a bit more easy. Good. Now we can also write out the dp prime. So we have p times p prime times rho plus 1 minus p prime 2 trace of rho identity. This is the first term. And now we have the second term over 2 p prime times identity plus 1 minus p prime divided by 2 trace of identity. And here, with sharp eyes, we already see trace of identity is 2. It's 2. So this will cancel with this. And then we have p prime plus 1 minus p prime, which is 1. So This is actually really just the identity. And that's good because our depolarizing channel maps the maximally mixed set or the identity always on itself. It's a fixed point. It should be. That's good. Oops. Alrighty. So now we can also write out this. P prime rho plus P1 minus P prime divided by 2. Trace of rho is 1. I will not write that. Identity plus 1 minus P over 2 identity. I hope you're all following because I'm not sure if I'm making a mistake. Let's see. Okay, now we can group that together. So we have P prime rho plus, and now I want to write that together. So we have 1.5 P minus P prime plus 1 minus P identity. And here we can see that the P just cancels. And we are left with 1 plus P prime. I'll just write it. 1 minus P prime identity. And I just showed you up there that I want to find the P prime such that rho comes out here. So can you read that off already? What P prime has to be? No? Nobody? So what I want is I want to recover only rho. So I want this to be 1. Exactly. Very good. So I want this to be 1, and I want this to be 0, no? So I know that P prime, so if this is rho, then that means that P prime is identity, meaning that P prime is actually 1 over P. Ta-da! Which is a very nice result, no? It's very easy. I would not have been able to derive that if I just looked at this measurement channel. So our inverse of the depolarizing channel is actually just the depolarizing channel of the inverse of the depolarizing strength. And let me tell you, this quantum channel is actually not a channel anymore, it's a quantum map, because it does not preserve our information flow. It's not a so-called CPTP map. It's not something that we could implement in our device. But we don't care about that, because what we want to use that for is in post-processing invert this measurement channel. And this we can do, right? We can do everything with maths that our heart desires, even if we cannot implement that in our device. Good. So we have our second box that we can fill in. Our inverse, of the measurement channel is actually the inverse, is the depolarizing channel with 1 over 3. The inverse of that is, thank you, actually 3. Okay, now we are out of time. I thought if I have time, I can show you this representation, but I will not do that. Instead, we will now do another interactive Slido quiz, where I would like to gauge a little bit how you found these concepts and how hard it was for you to follow them. This will not take long. I just want to see a little bit the mood of the room. Pew. Okay, then I will go to that one. And there's also a Q&A that you can see on the other tab. And I think, yeah. Ah, very good. Yeah, it's a probability. Right. So the depolarizing channel in this one direction, where it's 1 over 3, we can really interpret it as a probability. But when we go back, it's not anymore. That's what I mean. It's not physical. It's not something that we could implement. It's still the depolarizing channel, right? It's like, but good. It's not a probability then. Yeah, with 3. Okay, very good. So what was the hardest concept to understand for you? I can see the measurement channel. Good. The swap trick. Yeah. Also something very new that you probably saw the first time. think there are more. Ah, yeah, they are down here. My screen is a bit too slow. They're too small. Okay, I see the measurement channel is swap trick again. Interesting. Okay, very well. If you want, in the next lecture, I can do the calculation with sums over indices and then show you that it really works and how that translates again to this diagram. Would that be something that you would be interested in to understand the swap trick a bit more? Or do you say that was the hardest concept, but I still understood it? Okay, it looks like it's more the hardest concept, but not something that you want to dive into in again? No. Yeah? Yeah. So it's unique, yes. What I didn't say is that we need P to be non-zero. If P is 0, then we cannot recover what is lost. Else it is unique, I would say, yeah. Yes, because we just stringed, like in a conceptual way, the deep horizon channel just strings our quantum state into the Bloch sphere, but in a particular direction, right? And we know the direction, so we can just shrink it back or expand it back, which again, in a device you could never do because the information is lost, like, you know, dissipated in the environment. But well, on paper we can do that. Yeah. Okay, the measurement channel again. Good. Okay, so question to the people who said this was the hardest concept. Would you like to have more explanation next time? Or you just say, this is just the hardest concept. I'm okay with going on without recapping this. Okay. Yeah, a quick review? Okay, good. Then I will do a quick review in the next lecture. Very good. Now we come to the next one. Just to see it, like, because I wrote it down here. Okay, maybe I will just put it on the slide then, and then everybody can. Very good. Then I will recap that. Thank you. Okay, I mean, I can still, it will take 2 minutes. Very good, we have a question. What is the importance of all the ensemble in the classical shadows? Different ensembles can present different performances in the measurement process? Yes, very good question. So classical shadows perform very differently with different ensembles of measurements. And the Pauli measurements are not the only ensemble that we can look at, right? There are also other so-called POVMs that we could implement in the machine and then use this as a measurement ensemble. One very prominent example is the so-called SIG POVMs, which form a tetrahedral in the Bloch sphere. And these are an ensemble that we don't even need a randomization process in anymore. So the calculations even get a bit different in looking at the classical shadow protocol. So again, yes, looking at different ensembles leads to different performances. And we will see this difference very prominent when looking at global Clifford ensemble on multi-qubits and the local Clifford measurements on multi-qubits. Very good question. Thank you for that. Okay, next one. I can do that here. What was the easiest concept that you found in this lecture? Productive measurements. Yeah, it's very intuitive, no? We learn very quickly in quantum info or quantum computation what a productive measurement is. Pauli decomposition, yeah. Also, I think something that we are very familiar with. Ooh, tensor diagrams. Oh, cool. So some people like that and found that easy. Very nice. Nobody clicked measurement channel. I see. Cool. Okay, the Pauli decomposition is very clearly first place and then tensor diagrams, but can still change. Very good. Okay. And last but not least, is there another question? Ooh. Could you explain again, why do we need to invert the channel? Good question. I did not make that 100% clear because it's a little bit like weird in the beginning. But if we know the measurement channel, so what happens with our state after measuring many times, then we can, in post-processing, invert that. I told you that in the quantum state tomography protocol, in post-processing, we need to estimate all these observables, right? But instead of doing that, we invert the measurement channel. And then with this, we can act with it on the post-measurement state that we know would. So the protocol is we measure, and then we get out a tuple of a unitary that we applied and a bit string that we got. And with this, we can create the post-measurement state. And then when we act with the inverse of the measurement channel on that, then we know that this is a snapshot of our quantum state. This is one shadow, one glimpse into where this measurement tuple came from. And one snapshot is not enough because we're talking probabilities here. But if we now average over these snapshots, which again, we use the inverted measurement channel on, then we can do everything that we want, again, without doing full state tomography. I hope that was a bit more clear, but you will see tomorrow. In tensor diagrams, seems like we're always working with separable states. How to generalize? Yeah, also a good question. So if we work with non-separable states, we cannot really use this tensor structure, right? We only have these big boxes, but sometimes that doesn't matter. You will see in the next lecture when we look at the global Clifford measurement, we cannot separate these unitaries because they can be highly entangled, but we can still do nice things with that. Ooh, so many questions. Okay, I think we don't have time. I will go through them and then answer them in the next lecture. I would like to go to the next poll because we're running out of time, but I will save these questions. So if you could wish for what you want to see more in the next lecture, is it more coding? I mean, you will see more coding anyway. So more blackboard proofs, more presentation slides, or you're happy with whatever. Woohoo, more coding. Okay, 40% say they're happy with whatever. That makes me very happy because then I don't need to change so much in the next lecture. But okay, I see that you also want to be a bit more black body, so a bit more blackboard proof, so I'll take that into account. And I see that not so many people want more slides. Good. And yeah, I mean, coding will happen anyway tomorrow, so this will be anyway there. Okay, good, cute. Then with that, I would like to finish this lecture and thank you for your attention.